Okay, so let's go ahead and find a proof, or rather prove the derivative of secant x today. So the claim is that if f of x is equal to secant x, f prime of x is equal to secant x times tangent of x. Okay, let's go ahead and seek to prove this statement using the definition of a derivative as a limit. That's the way we do it around here. Okay, so f prime is going to be the same thing as the secant, or rather the limit, as h goes to 0 of the secant of x plus h minus the secant of x all over h. Okay? By definition. Okay, let's go ahead and write this as 1 over cosine of x plus h. I've got a plan. The limit as h trends to 0. This is going to be 1 over the cosine of x plus h. Okay. Correspondingly, we're going to write this as 1 over cosine of x. Okay, and then all of this is divided by h. So I'll just take all that and multiply it by the reciprocal 1 over h. Okay. Let's find a common denominator here. That would seem to be a good way forward. So we're going to have equals the limit as h trends to 0. Now I'm going to need to multiply this top and bottom by cosine x and multiply this top and bottom by the cosine of x plus h. And then I'm going to have that common denominator of cosine x times cosine of x plus h. Okay, so we got the limit as h goes to 0 of, it's going to come out to be cosine x minus cosine of the quantity x plus h. Okay, all divided by, there's an h down there too, let's not forget that, h cosine x cosine of x plus h. Okay, very good. So all of this now, nice and compact, right, over that common denominator. Okay, let's check our work, make sure that this is all free from error. Okay, looks good. Looks good. Now, I am going to use an expansion for cosine here, and I suppose I should zoom out one step before I establish this. We know that the cosine of a sum, or difference for that matter, so cosine of A plus or minus B, is going to be cosine A cosine B minus or plus sine A sine B. Okay, let's put a box around that. Now this has been proven in another video, so please refer to that. I'm going to be using it here to expand this right here. I don't think I'm going to expand the denominator value. You're going to see why it won't necessarily be so strategic to so do that. But I will expand the numerator, this term here in the numerator. So we're going to have the limit as h trends to 0. We're going to have cosine x, okay, minus, now the quantity, right, cosine x, cosine h, and so minus, right, because if it's plus, it's minus, if it's minus, it's plus, minus sine x, sine h. Okay, so all of that there, divided by h cosine x, cosine of x plus h. All right. Let's check that. Make sure we haven't committed any careless errors. Okay, looks good. Let's now go ahead and distribute the negative sign. So this is going to give us the limit as h trends to 0. We're going to have cosine x minus cosine x cosine h. Okay, plus, right, subtracting a negative, sine x sine h. Okay, all of that now, of course, divided by h cosine x cosine of x plus h. Okay, good enough. Let's take a look at that. Make sure we haven't committed any careless errors here. Looks good. Okay, looks good. Now, I am going to factor a cosine x out of the first two terms here, and we're going to have the following. This is going to equal the limit as h trends to 0. We're going to have cosine x, and then here next to it in parentheses, 1 minus cosine h. Okay, plus sine x sine h. And then, of course, all of that divided by h cosine x cosine of the quantity x plus h. Okay. All right, now, I am going to use the following property. A plus b over c is equal to a over c plus b over c. Okay, let's put that in the box there. That's the way we define basically division of a sum. Okay, this is something we take for granted, but it's true because that's the way we define it. And if you care to challenge your assumptions and learn, I suppose, how those assumptions matter, you'll study abstract algebra. Okay, but that's not for this video. But I am going to use it here. I'm also going to use the following limit property. The limit of a sum is the same thing as the sum of limits. So the limit of a sum is the same thing as the sum of limits. Okay. Good. Which is fairly evident why that would be. Okay. Limit properties are exactly as we would want them to be. Okay, limit of a sum, sum of limits. Limit of a difference, difference of limits. Limit of a product, product of limits. Limit of a quotient, quotient of limits. Limit of a function, function of a limit of a function. Okay, just as we would want, quite frankly. Okay, so I'm going to go ahead and use both of these properties in tandem here. So here we go. We're going to have the limit as h trends to 0. Okay, and we're going to have cosine x times the quantity 1 minus cosine h over h cosine x times cosine of the quantity x plus h, okay, plus the limit as h trends to 0 of sine x sine h over h cosine x cosine of the quantity x plus h. Okay. Alrighty. Now it's worth pointing out that the limit is dependent on h. The limit is not dependent on x. Okay. Now that being said, cosine x over cosine x is 1. Okay. And I can think about this as the limit as h trends to 0 of 1 minus cosine h over h times 1 over cosine of x plus h. You're going to see in a moment, I'll explain in a second why I'm doing this, why I'm expressing it this way, plus, okay, again, sine x can come out because this limit is dependent on h. It's not dependent on x. So this is going to be the sine of x times the limit as h goes to 0. Oh, but look, I can take a cosine x out too. Okay, which is tangent x, by the way, which is kind of what we're looking for here. Okay, this is starting to look pretty nice. And now it's going to be sine h over h. Again, I'll explain the strategy in a second. Times 1 over cosine of x plus h. Okay, let's zoom out one step. And now let me explain a few things. We know a couple of limits that are provided to us in introductory calculus. One is the limit as h goes to 0 of 1 minus cosine h over h. We know this is equal to 0. Okay, that's one of the limits that were provided. Now, in another video, I will explain why this is the case. I'm going to use a diagrammatical argument using the Cartesian plane. Okay, and those arguments are perfectly valid. Sometimes you have to rely on them, and it's what we basically do in when we study real analysis. We define a neighborhood. Okay, that's actually the term that we use, the mathematically correct term, a neighborhood around a region, around a point. Okay, but for now, I'm assuming that the viewer is comfortable with this. I'm also assuming that the viewer is comfortable with this. The limit as h goes to 0 of sine h over h is equal to 1. Okay, again, these two I will demonstrate the veracity of in a coming video, or videos rather, and I'm going to use a diagrammatical argument in each case. Okay, very good. All right, so this is all going to go away. I mean, obviously, this is going to 0. It doesn't matter what this is going to. And so we're left with just this. Okay, and sine x over cosine x is tan x. So let's establish that. Okay, limit as h goes to 0 of sine h over h is 1. Now, I suppose we should be clear that the limit of a product, I know I stated this already, but I want to be very thorough here, is the same thing as the product of limits. Let's put a box around that. Limit properties, we can also prove using real analysis and using diagrammatical arguments and discussion regarding neighborhoods and definable regions. But I'm assuming that if the viewer is watching this video, seeking to find a proof for the derivative of secant x, that the viewer is comfortable with limit properties and comfortable with these two limits here. Okay, so we can write it as tan x times the limit, just being very thorough here, as h goes to 0 of sine h over h times the limit as h trends to 0 of 1 over cosine of x plus h. Okay. Okay. All right, well, this is tan x. That's not going anywhere. Times 1 times, well, what happens as h goes to 0? Well, this goes to 1 over cosine x, which is the same thing as secant x. And we will go ahead and write that, rewrite that using the commutative property as we finish out our proof. Okay, there you go. Took a little bit more work than I thought it would, but we got through it. Hopefully you found this video to be educational. Hopefully now you understand not only how the derivative of secant x is equal to secant x tangent x, but why the derivative of secant x is secant x tangent x. Questions, comments, and concerns are always welcome. We also invite the viewer to leave comments regarding recommendations for future content. Have a great rest of your day, and we will see you in the next video.